here. I mean, you have made this workshop a great success. You bring in on many beautiful and exciting perspectives. So I'm Vasilis. Probably by now you know who I am. And today I'm going to talk to you about quantum Hall physics in the cavity. Things that we already saw in the morning by Jerome. And just a little bit of introduction of motivation, which is completely unnecessary after the talks of Jun Kono yesterday, and Jerome, and Johannes, and Joel, and everything. So in a cavity, we know that things are different than in free space because we're supposed to have strong coupling. And this leads to polaritonic states, which are hybrids between light and matter. And these have been seen like to lead to modification of material properties. And these are the things that are sort of making me excited while being here at ITAMP and doing research, like focusing on different aspects of these hybrid quasi-particles. The very exciting platform is, of course, polaritonic chemistry that Joel described, which was pioneered by Thomas Ebbesen and his experiments on chemical reactions. They saw this resonant modification of reaction rates, and this year, that's an important paper, I would say, that they saw the same resonant vibrational strong coupling and the modification of the reaction rates. And these are some of the key features that show up in this field. I will not talk about polaritonic chemistry, but I just want a little bit, because I will just come to it in terms of an advertisement later of some recent things that we are doing. And these are some sort of the key experimental features that show up, and some review articles that summarize them very nicely. But the focus of my talk today will be about condensed matter, and particularly to the electron gas inside a cavity. So here in this setting we have Landau levels, which Jerome obviously introduced yesterday. And in this situation we have this split ring resonator. And then you see that you have this very large avoided crossing here emerging. And this is the platform essentially in which the world record in light-matter coupling interaction has been achieved, which is above unity. It's what Jun Kono yesterday introduced as deep strong coupling. And since Jerome pioneered this platform, many groups now are doing the same, or at least more than one. And of course, the really exciting aspect of these systems is that now the FICE group is able to do transport experiments, and they see these amazing results on quantum Hall modifications, which I would say probably nobody really expected that would ever happen, since there are so many different kind of theorems telling you that this system must be topologically protected against anything. But nevertheless, this happens. So, so the outline of my talk now, so what I will try to explain you is like an exactly solvable model that comes from this work that we put out this year, together with G1, who is in the audience, has participated really a lot to this work, and he was very instrumental in it. Angel and Michael Rugenthaler, Marcus Pence, and John Suss. John was also around these days. So what I will show you today is how Landau polaritons emerge in these systems, which are collective hybrid quasi-particles between light and matter. And what I mean by collective, we are really talking now about the collective motion of electrons. It's essentially the cone mode of the system that couples ultra strongly to the cavity. And then what we will see is that because there is a reduction essentially of the cyclotron gap to the lower polariton gap, then what happens, what we call as weakened topological protection, because there is a gap reduction here. And at t equals 0, and if there is no decay channel in the system, no disorder, the polariton lifetimes are infinite and everything is perfect, then transport is indeed topologically protected. But once now, as you try now to allow to relax some of these assumptions, so you either put some finite line width to your polaritons, as you are seeing in this optical response spectrum here, then the polaritons are actually affecting the quantum Hall transport. And if you also allow yourself to go beyond absolute zero temperature, then also the thermal activation gap of quantum Hall transport gets modified, because at least intuitively, effectively, we can understand that this is controlled now by this lower polariton mode, which is softer than the cyclotron mode, which is the fundamental energy scale that is determining the activation gap, at least in the integer quantum Hall. So this is already the summary, and let's go into the actual details of how this it comes into play. So of course, the system we're having in mind is a 2D gas in a strong magnetic field, and then you have, of course, Landau level bands, which are completely flat. And these, we have the cyclotron transition, which is linear to the magnetic field. This, I guess, for this audience is just so boring. And now we just take this 2D electron gas, infinitely thin, and we put it into such a cavity, and we are also in the presence of a very strong magnetic field. This looks like a sort of Faber-Perot type of cavity, which in principle has nothing to do with the split-ring resonator of Jerome Feist, but this is a good starting point for us because it allows us to get polaritons, get an exact solution, and at least get some insight of what could be possibly happening in such a system on its transport. So the Hamiltonian from which we start is minimal coupling Hamiltonian, and here we really have n electrons. They couple to the external magnetic field. This is a classical external magnetic field given in the Landau gauge, so the field is perpendicular to the plane and constant. The momentum of the electrons also coupled to the quantized photon field, and now here we are taking into account only the perpendicular mode, the kappa z momentum, which has a polarization in the plane. And here, in order to couple to the classical magnetic field, we take them to be, the polarizations to be in parallel. And of course, this is described in terms of annihilation and creation operators, so the photons are quantized, but we only have one single mode. Unfortunately, we are poor guys, we cannot do macroscopic QED yet. And here, this is the energy of the quantized mode, and it's essentially an n-electron problem in a magnetic field and in a cavity. So it looks like a desperate situation, more or less. But actually, the situation is very simple. Why? Because the system is homogeneous. So we have free electrons in the plane. The system is, the thermodynamic limit is infinitely large. There is translational invariance. The cavity field is homogeneous. The magnetic field is homogeneous. And also the Coulomb interaction is translationally invariant. So what can you do then to describe the system is you go to the center of mass. This is the capital R coordinate here, the center of mass coordinate. And these are the relative distance. So these are the distances which are responsible for the interparticular interaction. And now, what happens in this, so this is an exact mathematical statement, and it's not some kind of approximation, it's just, it comes out of the assumption of a homogeneous Landau level problem. Then what you see essentially is that the homogeneous field, because it's homogeneous, does not see at all the interparticle interactions, and then it only couples essentially to the total momentum of the center of mass. And again, the center of mass, of course, experiences a magnetic field, which is now, this is the magnetic field that experiences the center of mass system. And the interparticle interaction, so the relative part of the system, this is completely decoupled from the photon field. So for anything that has to do with the cavity, so with the photons, you can essentially just integrate out the relative part and just focus into the center of mass, and you will be describing all photon matter phenomena. And these now are reduced just into the collective motion of the center of mass. Again, just to rephrase, this is an exact mathematical, you can just go by the algebra from one to the other. And since you have this type of Hamiltonian here, so you have essentially, this is like one harmonic oscillator, if you wish, so the total covariant momentum of the dynamical momentum of the center of mass, it couples to this other harmonic oscillator, and this is the energy of the cavity mode. You can essentially do a Bogoliubov transform, which mixes the electron and the photon operators, but then brings you into a non-interacting basis of upper and lower polariton modes, which are bosonic. And they are bosonic because they have the photons have coupled to the center of mass, which is a collective collective degree of freedom, which is bosonic in its essence. And of course, now here you have these polariton modes, which depend on the cavity frequency. This is the diamagnetic frequency, which depends on the particle number in the effective cavity volume. And the fact that we have it at this place and at this place is because we have the A squared term in the system. So what I'm saying is that if we would not have the A squared term here into the system, we would not have the diamagnetic frequency here, which is essentially renormalizing the polariton modes. So now if we plot these, and now we're taking some parameters from experiments, so this is typical densities in the Feist experiments and some effective mass, and we compute essentially here the polariton branch as a function of the magnetic field. We have the upper and the lower polariton branch. Now for these kind of parameters and for a cavity frequency of 0.14 terahertz, what you find is that the avoided crossing as normalized by the cavity frequency. Here is something like 0.33. So according to Jun Kono's definition from yesterday, this is in the ultra-strong light matter coupling. But you can tell me, so what? Even if I take a Jaynes-Cummings, I can still reproduce this avoided crossing. But this is not so accurate, because if I increase now the density more, things happen which are already quite deviating from Jaynes-Cummings or Davis-Cummings Hamiltonian, in a sense that you have this deviation of the upper polariton mode from the bare cavity frequency. So we have what is called the sort of polariton gap showing up. And Jun Kono was able to demonstrate the importance of this by getting this phenomenon that he called as the vacuum blow Ziegler shift, which has to do exactly with this shift of the upper polariton. And here, by making the density 5 times larger, we see that the avoided crossing becomes substantially larger, and we get this square root n with this square root scaling with the 2D density of the electron gas.
But classically, I can also get that shift that you call block-Ziegler shift, right? Like
of course, if you do transform matrix and you put all the parameters,
2D metal, you get that too.
Yes, you can do it. But here we're not getting by just putting a classical equation, but we are able to, at least to some extent, keep track of all of the degrees of freedom and like put the actual densities and all the parameters. So it's a little bit of an improvement to that. But I agree with you that these kind of modes you can get them. But at least I'm explaining you where this kind of physics is coming from. So. And now, of course, as Hoyle said, just looking at these polaritons is not such exciting. What is more exciting is to do some transport. So what I mean now by transport, at least it is falls within the Kubo paradigm. So I apply now an external time-dependent electric field in the plane. So I'm pushing the electrons now to move. So I'm pushing the cone mode of the system to move, the collective motion. And now I compute the optical conductivity, which we see here. And this is here now the current response function. And this is the current correlator, the time, the retarded one. And this is computed with respect to the fully interacting basis of light and matter, this average here, this expectation value. Okay? So we're not just using electronic and photonic states which are uncoupled. And now the interesting thing is that because, again, the system is homogeneous and so on, the transport process really happens into the center of mass frame. So you can really show that if you compute the velocity, the gauge invariant velocity from Heisenberg's equation of motion, so you take the commutator of the Hamiltonian with the position, and then you get the velocity, then what you see is that the momentum of the particle is, of course, the standard momentum operator of a particle, but it includes the vector potential, the magnetic field, and the cavity field. And now if you transform the total current operator, because in order to compute the current density, you need to sum over all the particles. If you transform this guy into the center of mass frame, you see that the total current operator only depends on the collective motion, so it depends on the center of mass, momentum into the photon field, and also to the classical magnetic field that the center of mass experiences. So what I'm telling you is that this current response function really only depends on the center of mass operator and on the photon operator. And this is exactly this center of mass Hamiltonian that I showed you before, where after you solve it via the Bogoliubov transformation, you go essentially, it depends, this current operator, only into the upper and lower polariton operators. So what this tells you that conduction properties in this system, they must depend on the polaritons because the total current is depending on these operators. Okay? And the cool thing is that since we have solved the system exactly into the center of mass states, into the center of mass frame, we can just use the exact center of mass states and compute these current responses and look into transport. And the first thing, which again is essentially equivalent to transfer matrix theory, you compute in this quantum mechanical way the response function. This is the longitudinal, the imaginary part of the longitudinal response function at 50 millikelvin. And we see here that the response is the upper polariton and the lower polariton and this avoided crossing that you see here. And of course, this Jerome Weiss has been seen for over a decade, and then Jun Kono and Uli Hubert and so on and so forth. Everybody sees these responses into their transmission spectrum. So for us, that was nice that we can get from this plain vanilla model of homogeneous system a nice description of these polarity composite particles, where here this is the value where the magnetic field is in resonance. The cyclotron frequency here is in resonance with the cavity, which is like 0.35 Tesla, as in Jerome's experiments, to keep it to some extent realistic, what we were showing. But again, Hoyle will say that this is again trivial, transfer matrix can do it, but what this allows us to do, having the Kubo formalism, is now to also look into the DC part. So we take now the frequency of the response function to 0, and now we look into the DC conductivity. And here I have the the Hall conductance, and this is the longitudinal conductance. And this is an ugly, complicated formula, but I'm showing this because at t equals 0, you can get these observables, these responses, fully analytically, because we have an analytically solvable model. Okay? And of course, here you see that the contribution that you get, of course, depend on the lower polariton and on the upper polariton, and these coefficients are just the coefficients that come into this Bogolyubov transformation, going from electron and photon into the polaritons. Okay? There are some rules and so on which they have to obey. These are detailed and not so insightful. But the thing that is important here now, if now on top of t equals to 0, I take the broadening parameter here. So we do response formally, so there is always some broadening parameter. If you take this broadening parameter to 0, so now the polaritons are sort of infinitely lived, then you can see very easily from the longitudinal part that once you take delta to 0, this goes to unity, this goes to lambda squared, and all of this cancels, and all of this becomes a unity essentially. So as you expect from topological protection, the Hall conductance is quantized, and the longitudinal is 0. So nothing essentially is happening at t equals 0 and for infinitely lived polarity quasi-particles. No surprise, essentially. And now what we will do next is just relax these two assumptions and look what happens. So now we take a finite broadening for these polariton peaks, which here is sort of a moderate value, like 1,000th of the cavity frequency, or approximately. And now we look into the deviations of the Hall conductance at two different plateaus. This is plateau 4, this is plateau 8, which correspond to these two different values for the magnetic field. And we look into the deviations from exact quantization. And what you see here essentially is that due to the finite broadening, now they are not going exactly to 0, so they are deviating because we have given a decay channel essentially to the polarities. Or they can somehow, they are not fully infinitely lived, so there is something happening to them, let's say. And you see now that actually this, since for different plateaus I'm putting essentially, I'm changing the magnetic field, so I'm changing essentially the point in which I am in the parameter space, you see that the deviations now vary, so they are not all flat, they are not all constant, and also as I make the cavity frequency smaller, the deviation is getting enhanced. And why is that? Because as you make the cavity frequency smaller, the lower polariton becomes lower and lower, so this is the mechanism of weakened topological protection. You are lowering the lower polariton gap, and that's why you are modifying more and more the Hall conductance. Okay? So what this shows you is that it is not just ultra-strong coupling that does the job, but you need some sort of finite lifetime or just a broadening parameter in order to be able to do anything beyond topological protection. So it's the combination of ultra-strong coupling and finite lifetime that will give you something. Okay? So you see that these deviations are very small, and it's one of the reasons most probably, or hopefully, if this theory has anything to do with experiment, that Jerome doesn't see anything yet on the deviations of the plateaus. But of course, this is under so many assumptions, so it's just a model that we are looking at. And now the next thing that we're trying to do now is to look into thermal activation. So now we relax the fact that we no longer just have t equals 0. We allow for finite temperature in the system. And what we know is that there should be an exponential, this exponential activation of the thermal activation, dictated by the gap, the lowest gap in the system. And in the integer quantum Hall system, this gap is just the cyclotron mode, the cyclotron frequency. But as I told you, in the polariton system, we have the lower polariton. So things now, since this guy is softer than the cyclotron mode, this activation should start to kick in faster. And for a quantitative description, again, we do Kubo formalism, and we just take the thermal ensemble and average over the different polariton states, and we compute the responses again. So here now I'm showing you how, again, so on the left-hand side we have the whole conductance for two different plateaus. This is, and for two different densities. This is the tuning parameter that gets you from plateau 8 to plateau 16, and we see now how they deviate essentially, or how they activate as a function of temperature. And what you see is that as you put more particles into your system, so by putting more particles you're enhancing the Rabi splitting, you see that the activation becomes faster with temperature. Why? Because you have stronger coupling, and again you are suppressing more the lower polariton, you're pushing it more lower. And at the same time, you also, here with the different colors, you see this is a larger cavity frequency, and this is a little bit smaller, and again you see that for the red line, again, activates faster because the cavity frequency is smaller. Again, this has to do with the fundamental value of the lower polariton gap. So the key message from these computations is that indeed the cavity suppresses the activation gap. This is done within the finite temperature cuboformalism, and indeed the cavity enhances the thermal effects in the transport. And yes. Yes. Completely? Okay, then I just summarize, and this is a question that Hoel asked me yesterday, but I leave it on the side. I also leave a little bit on the side the fact that we're also trying to do with Hossein here ultra-cold polaritonic chemistry. This is a couple of papers that we put out recently. And let me just give the outlook to the next things that we're trying to do now with Jerome. We're trying to test some of these predictions. And of course, on the theory side, we want to go beyond the homogeneous limit because it has fringes into the cavity fields. We want to include this disorder. But most of all, I would like to understand how I can compute this polariton lifetime. Where is it coming from? Because at the moment, I only use it as a parameter in the system. And with this, I would like to thank you all for your attention.
Very nice talk. So I just want to understand, your Kubo formula is done on a torus.
No, it's in a planar infinite
so
geometry.
You have edges.
No, we have no edges here. It's a fully bulk description.
No, but that's what I'm saying, in a torus. So
no, it's planar. No, planar infinite plane. It's planar geometry, infinite plane, infinite system, free space. It's the setting where the Landau levels also were obtained by Landau.
So then there are no edges.
There are no edges.
So that's why. Okay, yeah. So then it's an torus. Okay, whatever. Okay, so then the point is that there are no
planar
edges.
geometry. It's planar geometry. But the point is there are no edges.
Don't seem to matter in this.
Exactly. This is a bulk description. So
I think what I find really interesting in your case is that the Kubo formula, like the current, is also about the center of mass.
Yes, that's why
it follows also like what the optical response is about.
Exactly.
Which is not the case of the reactions.
Yeah,
right?
this is nothing to do with reactions.
Yeah. No, I see.
So while our next speaker is setting up, we'll take one more question.
Yeah, so simple question. I mean, you use a single cavity mode in the theory, as I understand.